we consider the heat transfer in a fully developed laminar unidirectional flow of a Newtonian fluid through a straight circular tube. In this particular geometry, we have an insulated section in which the incoming flow has a Poisson profile. After a certain point, we assume that the heat is input into the tube as a constant heat flux source. This could be, for example, a series of strip heaters which give the input flux. So the question is, what is the evolution of the temperature of the fluid flowing through the tube? In general, the flow will not be unidirectional. The reason being, there is a change in viscosity and density as the flow progresses in the tube. This is because the flow is continuously receiving heat through the walls. As the fluid heats up, the viscosity will reduce, so will the density. So there may be buoyancy effects in the flow, and apart from this, if the viscosity reduces, it will lead to an acceleration in the flow. And we all know through the continuity equation that if the flow accelerates, there will be no longer unidirectional flow, but there will be another flow perpendicular to the flow to make up for the acceleration. So the actual scenario will not be so simple. However, to make analytical progress, we may very well assume that the effects of changing viscosity and density are negligible as compared to the base flow. So therefore, in the governing equations, we assume that the flow is unidirectional. We assume that the density effects are negligible. Actually, you may wonder that if a flow is fully developed, then we should not have any effects of density. However, there is a hidden caveat in this. We have used the modified pressure in obtaining the Poisson profile. The modified pressure implicitly contains the effect of density because P prime or P bar, the modified pressure, is equal to the pressure minus rho Gz. And in this, we have the inbuilt density. In defining the modified pressure, we had assumed that the density is constant. If it is not a constant, meaning the density may change with temperature, and this dependency leads to additional body force in the Navier-Stokes equation, and this gives rise to a buoyancy force. Because we have assumed a steady state flow and a unidirectional flow, it means that the velocity profile is the classic Poisson velocity profile given by the pressure gradient G times a square by 4 mu times 1 minus r square by a square. This is the classic flow through a pipe, and therefore the governing equation may be written as u, which is the actual velocity, multiplied by del theta del z, which is the actual gradient of the temperature, is equal to kappa times the diffusion term. So the first diffusion term is the radial diffusion term. This is the radial diffusion of heat, which is 1 by r del r of r del theta del r, and the second term is del 2 theta del z2, which is the actual conduction term. In this expression, kappa is equal to k by rho Cp, where rho and Cp denote the density and the specific heat of the fluid respectively. K is the diffusion heat transfer coefficient, and kappa is called the thermal diffusivity or the thermal conductivity. For the sake of convenience, we can write down the velocity in terms of the average velocity or capital U, and the steps are very easy to follow. The average velocity is simply the integral of the velocity over the area divided by the total area. I forgot to write that down. So it's integral u dA divided by integral dA, and for a tube, integral dA is simply pi a square. And so if we do the calculation, we'll see that the average velocity comes out to be g a square by 8 mu. So in terms of the average velocity, the velocity field is given by u equals 2 capital U times 1 minus r square by a square. Thus, to sum up, the governing equation is 2u 1 minus r square by a square del theta by del z is equal to kappa times 1 by r del r of r del theta del r plus del 2 theta del z2. This equation is subjected to theta for z less than 0 is equal to theta naught, and for z greater than 0 at the wall of the tube, that is at r equal to a, we have k del theta del r is equal to q. You should be able to figure out the appropriate sign of q and the flux. In short, the incoming flux is opposite to the direction of the normal, and hence the minus sign cancels. But you should be able to figure that out on your own. And lastly, the theta is bounded at r equal to 0. Equivalently, one could have written the mathematical condition as del theta del r is equal to 0. But for analytical purposes, it would suffice to write down theta is bounded at r equal to 0.